Hi, in this talk, I will present our work, AutoCP, automated pipelines for accurate prediction intervals. We studied the problem of quantifying uncertainties of machine learning models' predictions in the applications of regression, classifications, and conditional arbitrary estimations in causal inference. We do that by constructing tight prediction intervals that cover the true label with high probability. In the standard settings of supervised learning, we denote the input features by X and label of interest by Y. We assume the training data D and the testing samples are drawn exchangeably from the same data distribution PXY. To split the data sets into a training set and a validation set, we construct a regression model on the training set. Then we validate the model on the validation set and use the validation results, such as residuals, to construct prediction interval. Such a way of constructing prediction intervals is called conformal prediction, which we will introduce later. Our goal is to construct prediction interval that cover the true label Y with probability at least the chosen coverage rate 1 minus alpha. We now introduce two concepts of validities of prediction interval. The prediction interval is called marginally valid if on average over the entire data distribution, the target coverage rate is satisfied. A stricter notion of validity is called conditional validity, that the coverage rate need to be achieved at every single X within the support of the data distribution. The conditional validity implies the marginal validities and much harder to satisfy than the marginal validity. In fact, conditional validities could not be obtained in any meaningful sense. It is only possible if the prediction interval has infinite expected width. However, there are works that partition the input space into subsets and using samples in each subset to construct a prediction interval. Then the interval is valid for each subset. Of course, dividing samples into subsets will inflate the interval width due to the sample scarcities in each subset. In our work, we aim to construct tight and marginally valid intervals. By tight prediction intervals, we mean on average prediction intervals are wider on the testing samples with larger conditional variance. As for two different values of X, the prediction interval width is proportional to the conditional variance of the label. Unlike the coverage guarantees, this conditional does not always hold. We want to do our best by tuning the machine learning models and conformal prediction algorithm jointly in constructing the prediction intervals. We will do this by automating machine learning methods, which tries to keep human out of the loop, that allow machine learning practitioners to use machine learning model with valid intervals. Before we introduce our AutoML framework, we will introduce a few conformal prediction algorithms included in our framework. Split conformal prediction, SCP, is the simplest conformal prediction method that is able to construct marginally valid prediction interval. Suppose we split the dataset into two equal-sized subsets, I1 and I2. We feed a regression model to I1. Then we define a non-conformity scores as the residuals of mu I1 on a sample X and Y. We compute the residuals of mu I1s on all the samples in the validation set I2. We let the set I2 collect all the validations residuals. Suppose Q 1 minus alpha is the 1 minus alpha quantiles of the set Ri2. Suppose there is 100 residuals in Ri2 and alpha equals to 0.05. Q 1 minus alpha is the fifth largest residuals in Ri2. The interval of SCP is given as subtracting and adding Q 1 minus alpha to the mean estimate is mu I1. The interval given by SCP has constant length over the input space, in other words, non-adaptive locally. As shows in the left panel, the interval of SCP is 2y when X is between 0 and 2, where the conditional variance of Y is very small. Local adaptive methods such as locally weighted split conformal prediction can do better than SCP by estimating the conditional variance of Y. There are two classes of approaches to construct locally adapted prediction intervals. First, as in the locally weighted split conformal prediction. change the non-conformity score from residuals to inverse variance weighted residuals by introducing a conditional variance estimator sigma fitted to I1. Then we construct the interval with Q1 minus alpha times the conditional variance, which is adapted locally. We can also consider changing the mean estimators to the quantile estimators Q hat. Then the non-conformity score is the outer quantile's residuals. Because of the gap between the upper quantile and the lower quantile is adapted locally, the interval given by the quantile estimators is also adapted locally. There's a second class of solutions. Instead of splitting the samples into two flows, you can also split the samples into multiple flows to construct the prediction intervals. The two classes of methods can be combined together to construct tighter prediction intervals. In practice, the workflows of using conformal prediction could be complicated. We need to choose the underlying machine learning models and the type of estimators and the collaboration methods. If you want to construct the best prediction intervals, we will need to optimize many hyperparameters. Motivated by this, we develop AutoCP or AutoML toolkits to solve the model selection problem in building conformal prediction pipeline. Given a data set and a target coverage rate, AutoCP start by choosing a collaboration method, split samples into subsets, then choose the ML model and estimator and non-conformity score to construct the prediction interval. The interval length would act as a feedback for AutoCP to learn what pipeline you should try in the next run for minimizing the interval length. Given a list of models, the space of all possible pipelines is the product space of the model, estimators, and collaboration method. An example pipeline is random forest, quantile estimator, fivefold cross validation, and all their hyperparameters. We want to find a pipeline that minimizes the average interval length on the validation samples. Its objective is a relatively high-dimensional black box function and has no closed form solution. To solve the black box functions optimization problem efficiently, we use Bayesian optimization with the divide and conquer strategies, in which we model the interval length for each model separately by using a Gaussian process regression model. We assume the kernel in the Gaussian process are additive. In other words, high-dimensional functions can be decomposed into some low-dimensional functions. We optimize the kernels for the estimators and collaboration method jointly across different models. Finally, we model computational time by a separate Gaussian process model. In model acquisitions, we learn to prioritize the pipelines with low complexities. We will only evaluate expensive pipelines if there is performance gains in using them. By doing so, AutoCPs converge to the optimum pipelines faster than the standard modeling approach in Bayesian optimization. The type prediction intervals have two advantages. First, suppose we fix the target coverage rate. If the prediction intervals are tighter, we are more certain of the true value of the label. Second, suppose we only accept the predictions if the associated intervals are shorter than a certain threshold. In this case, we will make fewer mistakes and more samples will be in coverage. Finally, in experiments, we compare AutoCP with the existing conformal prediction algorithms in the literature. All the methods achieve the same target coverage rate, but AutoCP does it with the shortest average interval length. Conformal predictions can be applied to the problem of conditional arbitrary by estimation, basically estimating the difference between the treated and control outcomes for given individuals. You can apply the conformal predictions on the regression model of the treated and control outcomes respectively. We apply AutoCP to two datasets in causal inference. Among the method that satisfies the target coverage rate, AutoCP achieves much shorter interval length. Thank you for watching. If you're interested, take a look at our papers on our website.